In today's lesson, we are going to continue to look at special triangles. We're just going to be kind of adding more concepts to those two triangles and their angles and associated side lengths. So just a review of those special triangles. We have the isosceles triangle with two 45-degree angles and a 90-degree angle. It is a right angle triangle. And we have both legs being 1 and the hypotenuse being √2. And then the half equilateral triangle with angles 30, 60, and 90, the hypotenuse being 2, and the legs being 1 and √3. Again, for our angles, 60 is in the bottom corner, so the adjacent is 1 and the opposite is √3, and 30 is up top, which makes 1 the opposite and √3 the adjacent side. So again, we're going to use these angles. We're going to be using the ratios in some new concepts. Before we get into those concepts, though, we do have to look at some new terminology. So we are going to look at the terminal arm and the initial arm. So this is going to help us kind of identify angles or label angles on a Cartesian plane, right? So almost think of like a grid system with a y and an x. Right? So the initial arm is the first arm of an angle drawn on a Cartesian plane that meets the other, or the terminal arm of the angle at the origin. So it always meets kind of at this origin of 0, 0, and it's always at 0 degrees. So it's flat, horizontal, and it's in the right direction, and it's not elevated or anything. So that's our initial arm, and it does not move. So it's always going to stay in this position. The terminal arm is the arm of the angle that meets the initial arm at the origin and rotates around the origin counterclockwise. So say counterclockwise to form a positive angle. That means if I started this arm, I go counterclockwise to the terminal arm for a positive angle. So I start at the initial, I move counterclockwise to get a positive angle by reaching the terminal arm. I could also go clockwise and make a negative angle. So it's either counterclockwise for positive or clockwise for negative. So kind of opposite of what you might think. Right? And this helps me determine what theta is, depending on how I want to refer to it, either in a positive way or a negative way. Usually we always kind of see the positive form, but not to say that we can't see the negative as well, but usually we see the positive. So we can use reference angles to help us find trig ratios for obtuse angles. Right, most of our trig ratios that we've dealt with have been right angle triangles. We do have some laws that we'll look at later for obtuse angles in terms of a non-90 degree or non-right angle triangle. But we're going to look at using some of our special triangles to help us for obtuse angles. So any angle over 90 degrees does have a reference angle. And the reference angle is between 0 and 90 and helps us determine the exact trig ratios when we are given an obtuse angle. The reference angle is the angle between the terminal arm and the closest x-axis, whether it's 0 or 360 or 180. Right? So it's always in reference to the x-axis. So even though our initial arm is always going to be pointed in this direction, the reference angle is going to be anything we're always going to be going to the closest angle here. So even though the angle is actually 120, let me just highlight around the blue one. So even though our angle is 120, we can use a reference angle of 60 to help us determine the exact values of this terminal arm or of this measure or of this angle. Another thing that we're going to learn to kind of help us with this is what we call the cast rule. And when finding the trig ratios of positive angles, we're rotating counterclockwise. So we already mentioned that. We're starting at 0 and going counterclockwise from 0 towards 360. The cast rule helps us determine which trig ratios are positive in each quadrant. So based on what the trig ratios are, depending on where it's located or where our terminal arm is located, our ratios may be negative. right? So this cast rule kind of helps us figure out what the ratio should be based on whether the ratio is going to be positive or negative. Right, so let's go through a couple examples to kind of help us with this. Right, so we want to find the reference angle for 250 degrees. So what we're going to do, I'm going to draw my initial arm first. So initial arm is here. 250 degrees means we go 250 degrees. We use green. So 250 degrees is going to be somewhere over here. So that means this is 250 degrees. It's a positive, so that's how we'd measure it, going from the initial arm counterclockwise to the terminal arm. Now for the reference angle is going to be the angle going from the closest x-axis. So that means this angle here. So this angle here, let me just actually spread this out a bit more. So there's the angle, it's 250 degrees. The reference angle that we're going to use is this angle in here. So to figure out that reference angle, right, we're going to take 180. We are going to use 180, but we're going to take 250 minus 180 degrees, and that is going to give us 70. So that means the reference angle that we're going to use is going to be 70 degrees. That reference angle of 70 degrees is what we're going to use to help us come up with the ratios, so to speak. For 120, again, draw my reference, or my initial arm is here. 120 is going to be, say, somewhere around here. So there's my terminal arm. I'm going to draw the 120. So 120 degrees. The reference angle is going to be to the closest x-axis, so this angle here. And to figure out that angle, I can do 180 minus 120, and I get 60. So this angle is going to be 60 degrees. So that's going to be my reference angle. And you might see where we're going to go with this, but if I know that it's going to be 60 degrees, or if I know that there's going to be a right angle triangle with 60 degrees, I'm going to reference my special triangles that we learned in the previous lesson. 300 degrees. So again, let me draw my initial arm. So my initial arm, my terminal arm is going to be somewhere around here. Again, it's just kind of a sketch, so it's not terrible if it's not completely accurate. I'm going to go around, so that's 300 degrees. The reference angle is going to be the closest 90-degree angle, or closest x-axis, so this angle here. And to determine that, 360 minus 300 equals 60 degrees. So this angle here is 60 degrees. Now keep in mind, it's just the reference angle. So even though you might think it's going counterclockwise, we're not doing that. We'll talk about that in a later lesson or in a later example. We're just looking at the angle between the x-axis and the terminal arm in this direction. And finally, 225 degrees. So again, let me draw my initial arm. My terminal arm is going to be somewhere over here. Rotate around 225 degrees. So let me just make it a little bit spread out a bit more, just so I can kind of come here. So my reference angle is going to be here. And to figure out that, 270 minus 225 equals 45 degrees. So that means that this reference angle is going to be 45 degrees, which is one of those angles from a special triangle. So I could use that to help me figure out what the ratio of the sides would be, or what the sides might be, or how long that terminal arm might be. Again, different things, different applications that we're going to look at later on. Example 2, so now we're going to look to try to find the exact values. Right, so I want to find the exact value of sine 45. We've done something similar to this before with our special triangles, but now we're looking at kind of a Cartesian plane. So I'm going to draw that angle. So my initial arm, My terminal arm is here, and it's 45 degrees. I don't have to worry about doing a reference angle because I'm in this kind of general location, right? This is the angle to the closest x-axis, so I don't have to come up with another reference angle. Because of the angle of 45 degrees, right, that should indicate, okay, there is a special triangle associated with this. So I can actually, let me pick a color, go purple. So I can actually imagine that there is a right angle triangle with 45 degrees. That means the other side is 45 degrees, which makes an equilateral or an isosceles triangle. This matches our special triangle, so 1 and 1, and that means that this is root 2. Right? Again, is it at what it's going to be? Maybe, maybe not. But because we know this angle and we're making it a right angle triangle, we know that any other triangle is going to be similar to this, just maybe a different factor. But it all kind of boils down to the same thing. So in this case, then, sine 45 is going to equal opposite over hypotenuse, which is equal to 1 over root 2. So again, similar to what we've done before, we just kind of had to make this our special triangle. Now, sine of 120 or 220 or 210. I'm going to draw my initial arm. Initial arm is here. 210 is somewhere in this direction. I'm going to draw in 210. I'm actually going to take that out though because I'm going to deal with my reference angle. Right? So I'm not dealing with this actual angle. I'm going to deal with this reference angle here. So if the entire thing is 210, then 210 minus 180 equals 30. So this angle here is 30 degrees, which is one of those special triangles. So if I make a right angle, I know that it should be, right, 30 degrees. That makes this 60 degrees. So then that means root 3, 1, and 2. However, this is not in the same location as we were before. So this is actually a negative root 3 because we're in the negative direction, so to speak, in terms of like coordinates. Right? If 0 is at the center here, then we're in the negative, and we're going down, so that's a negative 1. So our ratio isn't going to be the exact same as it would if it was a positive. The ratio for sine of 210 or sine of 30, because that's the reference angle we're using, right? It's going to be opposite over hypotenuse, which is negative 1 over 2. So the sine of 210 is actually equal to the sine or negative the sine of 30. And the reason I know this works, or kind of how I know that this ratio is correct, is because if I think about the cast rule that we mentioned earlier, with C, A, S, T, this angle is in the T quadrant, which means that only tan is positive. And if I look at my sine ratio, it's negative. So it does make sense that I have a negative ratio in this quadrant for sine. Cosine of 240. So I'm going to do similar things. I'm going to go through. I'm going to draw my terminal or my initial arm. Just for reference, I'm going to draw my terminal arm. 240 is somewhere over here. Right, so if this is 240, I want my reference angle. So the reference angle is going to be 240 minus 180, which is equal to 60. So I can get rid of that larger angle. I'm only going to deal with my reference angle now. So 60 degrees. I can make a right angle triangle. That means root 3, 1, and 2. because it's cosine, cosine is equal to adjacent over hypotenuse, which is equal to 1 over 2. However, I forgot to make sure that because I'm in the negative, right, I'm going into the left, in this case of the origin, that's going to be a negative 1. And because I'm going down, it's going to be negative root 3. So this is actually going to be negative 1 over 2. Or I could think of it as cosine 240 is equal to negative cosine of 60. Because of that negative ratio. And again, that does make sense because again, C, A, S, T, only tan is positive in this location or in this quadrant. For D, tan of 315. Again, I'm going to draw my initial arm. My terminal arm is going to be somewhere over here. My reference angle is going to be here. To figure out that reference angle, 360 minus 315 equals 45 degrees. This is 45. Oops, If I make a right angle triangle, you can see it's going to form a special triangle with 1, 1, and root 2. But the base, so to speak, or this top one here, that's going to be positive. That's in the positive direction. But this one over here is going to be negative because it's going down. Right? So you can think of it that way. For tan, tan is opposite over adjacent. The opposite is negative 1 over 1, or just negative 1. So tan of 315 is equal to negative of tan 45. And again, makes sense because C, A, S, T, only cosine is positive in this quadrant, so it makes sense that the tan ratio is going to be negative. Right, so we didn't really use too much of the cast rule here, just more for reference and more for just determining or just kind of reinforcing the idea of what our ratio should be, whether it's positive or negative. We will look at it later on, and that will help us kind of figure out where certain angles are going to be, things like that. But so far we've talked about rotating counterclockwise. We can also rotate clockwise from the x-axis, but the angles are going to be considered negative. So for example here, right, kind of going from my terminal or my initial arm, we had usually our positive value would be 315, but we could also go in the other direction and make it negative 45. So negative 45, if I said angle of negative 45, that means the same thing as an angle of 315 degrees, right? So just different ways of referencing it, which when we're talking about what that angle is, not the reference angle, right? So even though when we're looking at some of these ones, the reference angles, it might look like we're going clockwise, so it should be negative. We're only talking about in reference to reaching that terminal arm. Right? So in terms of referencing that angle. So let's take a look at what we kind of mean by that. So sine of negative 45. Right? So if I want sine of negative 45, that negative, let me draw my initial arm here. So negative 45 means I'm going backwards or clockwise 45 degrees to my terminal arm here. So if that's negative 45, I don't have to worry about my reference angle because I just know that this is going to be 45. If I make a right angle triangle, because again I want to find the exact values. Right angle triangle with an angle of 45 also means that we have 1 and 1, or 1 and negative 1, because it's going down, and root 2 for our hypotenuse. So sine is opposite. Sine is opposite over hypotenuse, which is negative 1 over root 2. Or we could say that sine of negative 45. Sine of negative 45 would be the same thing as sine of 315. Because again, that's the same thing as this angle here, 315. Just the positive version of it, which is the same as the sine of negative, or the negative sine of 45. For B, cosine negative 60. So cosine of negative 60. I'm going to draw my initial angle here. Terminal arm is going to be somewhere over here because negative 60 is coming in this direction. So that means even though it's negative 60, that means this reference angle is still going to be 60 degrees. Right angle triangle. It is going to make a special angle or special triangle. So root 3, 1, and 2. Or negative 3. For cosine, cosine is adjacent over hypotenuse. So adjacent is 1 over hypotenuse, which is 2. Right? So that means I have a positive ratio, which makes sense because of, again, if we wanted to go and label the cast rule, CAST, cosine is positive in this quadrant. So I can say that cosine of negative 60 is equal to the same as cosine of 300, which happens to be the same as cosine of 60. Right, so a lot of kind of similar angles that will give us the same cosine or the same ratio. And lastly, tan of negative 240. So I'm going to draw my initial arm here, negative 240. So negative 180. So 240 will be somewhere in here. So negative 240. Or I could think of, if it's negative 240, then it would have to be a positive 120. Either way, my reference angle here is going to be 60. I'm going to the nearest x-axis. Form my right angle triangle. I have then root 3, 2, and 1. It's negative 1 because of the it's on the left of the origin. Tan is opposite over adjacent, which is root 3 over negative 1, or negative root 3. It makes sense that we have a negative ratio because, again, in our cast rule, CAST, only sine is positive in this quadrant, tan is not. So I can write that tan of negative 240 is the same as tan of 120, which is the same as negative tan 60, because it's the negative tan ratio here. Right, so a lot of different ways that we can kind of go through and figure this out. If we can, once we start to recognize these kind of relationships with a lot of the special triangles, then we can kind of easily figure out the exact values of those ratios. Right, so that's all this really is, just determining the exact values. Just easier ways of determining the exact values.